Hello everyone. The IMO 2023 took place over the past weekend in Japan, and today we'll be taking a look at the day 1 problems, which include a really fun problem tree. But before we take a look at the problems, I have some photos from the event itself to show you. So these photos are taken from the IMO 2023 Instagram page. And over here we have photos of some of the contestants arriving at the Japan airport. And on Friday, the day before the contestants had the opening ceremony. So over here is a photo of the contestant waiting for the opening ceremony to begin. And this is my favorite photo of them all. It looks like the contestants have some time to even have fun at the arcade before the contest itself. So without further ado, let us take a look at the problems. So for problem 1, we are supposed to determine all composite integers n greater than 1 that satisfy the following property. If d1, d2 until dk are all the positive divisors of n, and they are arranged in increasing order, then di divides di plus 1 plus di plus 2 for every value of I. So we have the divisors here in increasing order. d1 is 1 and dk is n. And for each divisor, it divides the sum of the next two divisors. So there are a few possible ways to approach this problem. I'll share the solution, which I think is the easiest to motivate. So usually when you have a condition like this, you will want to investigate applying the condition at the front or at the end. And in this case, applying at the front doesn't tell you much because 1 divides everything. So let's apply the condition at the end, which gives us dk minus 2 divides dk minus 1 plus dk. And the crucial step is to remember that all these are divisors of n, so dk minus 2 divides dk as well. And once you write this down, it's very easy to see by taking the difference that dk minus 2 divides dk minus 1. So this gives you the divisibility condition here. And once again, all of these are divisors of n, so we also have dk minus 1 divide dk. So once you write these two down, the natural hypothesis is, does this divisibility condition apply all the way down? And unfortunately, at this point, you're stuck because if you want to use the given condition one step down, you have dk minus 3 divides dk minus 2 plus dk minus 1, but you do not have the second line, dk minus 3 divides dk minus 1, unlike in over here. So right now you do not seem to be able to progress further downwards. However, the natural thing to try then is, can I progress upwards? So fortunately, 1 divides everything, so d1 divides d2. Do I have d2 divides d3? Well, if you look a little harder, actually you realize that you do, because the divisors on opposite ends are actually related to each other. They will multiply to give n. So in this case, d2 is n divide dk minus 1 and d3 is n divide dk minus 2. And because we have this divisibility here, the mirror image consequence is that d2 divides d3. So indeed we have this divisibility condition here. And now when you have something like this, you must remember to cash in on the given condition, which is d2 divides d3 plus d4, so that we get d2 divides d4. And once we have this, we realize that we can take the mirror image to get what we were missing beforehand. dk minus 3 divides dk minus 1. So together now we have dk minus 3 divided dk minus 2, which gives this divisibility here. And again, we take the mirror image, we have d3 divides d4, and so on and so forth. So by extending this logic inductively, you'll be able to reach the required strong necessary condition that we have di divides di plus 1 for all values of I. So once we reach this part, it's quite natural to guess what are the possible solutions. So let's take a step back, put aside this solution for now, and start afresh. We hypothesize that n equals to power of p works. And indeed, if n is a power of p, then the divisors are all that power of that p, but in increasing steps, right? And some p to the a, does it divide p to the a plus 1 plus p to the a plus 2? Of course it does. So this shows that n equals power of p works. And then on the flip side, we now need to show that all other values of n does not work. So if n is not a power of p, it will have at least two distinct prime factors. Say two of them are p and q, where p is less than q. Then, now we pull back our necessary condition that we have deduced previously. We need this to hold. And the problem here is, where can q be? Q needs to appear somewhere in this chain. Say the position is at dl. But L needs to be at least 3 because D1 is taken by 1. P is less than Q means P must appear before Q. So Q cannot be at D2. So this is Q is at least at position 3 and above, which means that the divisor before that is not 1, and it cannot be Q itself again. So DL minus 1 will not divide DL, which contradicts our necessary condition here. So this means that all the other values of n indeed do not work. So that is all there is to problem 1. What do you think of this problem? I know some contestants felt that this problem is way too easy as a problem 1. So let me know what you think in the comment section below. Okay, we will now take a look at problem 2, which is a classical geometry problem. After reading each statement, I will point out the relevant parts of the diagram so that it's easier to follow. Let ABC be an acute angled triangle with AB less than AC. So we have ABC here. Let capital omega be the circumcircle of ABC. So this is capital omega. Let S be the midpoint of the arc CB of omega containing A. So this is the arc CB containing A, and S is the midpoint. The perpendicular from A to BC meets BS at D and meets omega again at E. So this is the perpendicular. It meets BS at D and it meets the circle again at E. The line through D parallel to BC meets the line B at L. So this is the line through D that is parallel to BC and it meets BE at this newly constructed point, which is L. Denote the circumcircle of the triangle BDL by little omega. So this is the circumcircle. Let little omega meet capital omega again at P. So these two circles intersect. I call this point P. Prove that the line tangent to omega at P meets the line BS on the internal angle bisector of angle BAC. So this is the tangent at point P. It meets the line BS at a certain point, which I call X. And we are supposed to prove that X lies on the internal angle bisector of angle BAC, which is the dotted line. Now, one thing to note is that I constructed the point S prime here, which is the diametrically opposite point from S. And in doing so, because S is the midpoint, so S prime is also the midpoint of the arc BC, then in fact AS prime is the angle bisector of angle BAC. So that gives us something more concrete, a more concrete way to describe the angle bisector. So the question is to show that A, X and S prime are collinear, or X lies on AS prime. Now this is actually quite hard to prove because X is defined in terms of the tangent, which is sitting in the middle of nowhere, and showing collinearity is in general not so easy to prove. So instead we'll flip the problem around. We'll instead say we have the angle bisector AS prime and we define X to be the intersection of AS prime and BS, and then prove that PX is tangent to omega. So notice X now, I define it to be this intersection, and then I have to show that PX is tangent to omega. You might say that proving that PX is tangent is again quite a difficult problem, but I can convert this condition to the power of point condition. So I need to show that XP square equals xd times xb. So this is about length, it is much more tractable. So I placed this here as a reminder that we have flipped the problem and we need to show this. Okay, what's first? Well, I'm going to introduce the point A prime, which is diametrically opposite from A. And why might I want to do this? Well, firstly, because AA prime is the diameter, AEA prime is a right angle. And we have EA prime is therefore parallel to BC and LD. So it introduces this parallel line, which seems to be a useful thing to do. And more importantly, actually, I am now going to claim that P, D, and A prime are collinear, which gives a very nice way of describing P in terms of points D and A prime without caring about this outer circle here. So to prove this claim, I'm going to use Rheims theorem. This theorem is quite easy to prove by basic angle chasing, so I will not bother showing it. But essentially, to recap what the statement says, is that if you have two circles that intersect at M and N, and we have a line passing through M, intersecting the first circle at A1, second circle at A2, and if B1 is a point on first circle, B2 is a point on the second circle, then A1, B1 parallel to A2, B2 if and only if B1 and B2 are collinear. So if you're unfamiliar with this theorem, do feel free to Google, it's quite useful. But let's apply it in our context here. So P and B are the intersection points of the two circles. L is on one circle, E is on the other circle, and LB is a straight line. In this case, D is on one circle, A prime is on the other circle, so LD parallel to EA prime implies PDA is a straight line. So by applying this theorem, we have our claim that indeed PDA prime is collinear. So once again, this gives a very useful way to understand P, because A prime and D are quite, I would say, native or basic points in terms of the capital omega. So it gives us a better understanding of how P is. And at this stage, we will need to do a bit of angle chasing. Basically, the motivation is because we want to eventually reach something like this, and it looks like something about similar triangles might help us. So let's take a look at triangles that are related to X and see what form of angle chasing we can do. Well, we do have the following. We have ABX, because this is using the concyclic property, we have this right angle here is equals to this right angle. And then now using the fact that SS prime and AE are parallel, we have this right angle equals the other right angle. So these two equality angles and the common point X gives us a pair of similar triangles. Indeed, we have AXD is similar to BXA. So once again, the right angles are equal and X is the common pivot point. So the two triangles in blue are similar. And this tells us that we have the ratios AX over XD equals BX over XA, which I can rearrange to get XA squared equals XD times XB. So we have the right hand side appearing here, which means that all we need to show now is XA equals XP. This is very nice. XA and XP is much more tractable than this thing with 4 terms here. Okay, what's next? XA equals XP. Well, if you try to do a bit more angle chasing, X seems to be in the middle of nowhere, so it seems a bit hard. But if you stare at this configuration, there's something very suspicious looking here. It might remind you of this lemma from geometry, that if you have a right angle triangle, and this is a point on the hypotenuse, then 2 of the lengths equal will give you the third length being equal. So there are various ways to prove this, but the mnemonic to remember this is that this basically can be seen as being part of a circle. The circumscribing circle will have this as the diameter, and then these three are all the radius. But of course, you can go and look up how the proof goes. But this is a common lemma from geometry. And in this case, we do have AP, this part here, right? AP to A prime. This is a right angle because A prime is a diameter. So our funny looking triangle here is actually here, APY. We have a right angle, and we want to show that AX equals XY, because then we'll have AX equals XP equals XY equals the radius of that circumscribed circle. So we have further converted the problem now to showing that X is midpoint of AY, which arguably is nicer because we are now dealing with points on a straight line. But still, this green segment, AX equals XY, is not very friendly because it seems to end in the middle of nowhere. So instead, this motivates us looking at the blue segment instead. So this is why I had to shrink my diagram a little, but basically we consider the point A prime S extended and the point DA, let them intersect at the point Q. So once again, this is quite natural because DA extends to now Q, DX extends to S, and DY extends to A prime. We might be able to convert AX and Y into relations between Q, S, and A prime. And indeed, the green line is parallel to the blue line because AS prime, A prime S is a rectangle. We have all these 90 degrees going around due to the diameters. So this line is parallel to this line. So once we have the parallel lines, then to show that AX equals XY, it suffices to show QS equals SA prime. And once again, we have our suspicious looking right angle triangle. This time it is QEA prime being the right angle triangle. I've already showed that this is a right angle because AA prime is the diameter. So at E, we have a right angle. So this right angle triangle, we want to show QS equals SA prime. We convert that to being suffices to show that ES equals SA prime. So to show this, we just need to do one last bit of angle tracing. Firstly, this red angle is equal to the purple angle because these are the two radiuses of the circle. And now we have this red angle equals this red angle because of the concyclic property. And this purple equals that purple because of the concyclic property. So red equals purple, so this equals this. And this is perpendicular bisector of BC, this is midpoint. So in essence, you have ES and A prime being reflection about the point SS prime. So ES equals to SA prime. So that is all for problem 2. It is quite a nice classical geometry problem. There are quite a few steps involved in the solution, but some contestants felt that it is also nothing too sophisticated. So what do you think of this problem? Let me know in the comment section below as well. And finally, let us take a look at problem 3, which has generally received positive reviews from the contestants as being a fun and interesting problem. So for this problem, we have the following. For each integer k greater than or equal to 2, determine all infinite sequences of positive integers a1, a2, and so on, for which there exists a polynomial of the form px equals to a k power polynomial monic, and all the coefficients are non-negative integers, and such that p of an equals to the product of the next k terms in our sequence for every single value of n. So it's a bit confusing, but I'll give a bit of motivation in how you might come about with the solution. So first of all, Rather than approaching this this question like this, where you need to find all sequences such that there exists a polynomial that fits the condition, we can flip the problem on its head and say, for a fixed polynomial of this form, what are the possible infinite sequences that will satisfy this recurrence for every n? And then once we take the union of all valid sequences across all p's, then we will have the global list of nice sequences. And once you phrase the problem this way, that leads you to consider, can I start thinking about the problem with some simple p's? So start simple. Let's consider the polynomial px equals to x to the k. What are the possible infinite sequences that will satisfy this recurrence? Well, if I write the recurrence out directly, I have this expression here. And this is a product of k terms. This is a product of k terms. So you expect some terms to be bigger than, some terms to be smaller than, or some terms equal with an. But what happens if all of them are like bigger than an? Then you'll be in trouble, right? So that leads you to think about the scenario where maybe let's zoom in on the minimum, at the minimum point of the entire sequence. If m is the index such that am is the minimum in the entire sequence, then all these terms after that, all these, the next k terms, right, they are greater than or equal to am by definition of minimum. You cannot have anything that is strictly greater than, because then it will violate this equality. So this forces the next k terms to be equal to am. And you can repeat this logic forward to show that the sequence is constant after that. And similarly, you can repeat the logic backwards by sliding the window one at a time. You can very easily show that the sequence is also constant before that. So it seems that looking at the minimum has led to a decisive conclusion of what the sequence can be. So carry on with this motivational talk. Don't worry, I'll make everything rigorous later in the solution. The motivation then leads us to think about this question. Is it possible that if we think about the minimum element as looking around that minimum element, will that force a certain requirement on the sequence? So if we look at a general polynomial, unfortunately, if we say m is the index where am is minimum, you cannot really repeat the previous logic in this context, because now this can be a lot larger than just an to the power of k. You have all these other extra terms here. So no issues with these things being like bigger than am. So you seem that you're stuck. But the thing about minimum is it is minimum to the left and to the right. What I mean by this is we can think about the element before that. So if we assume that m is bigger than 1, so there is an element before that, and we assume that this is not a tie, then am being minimum means that the element before that is strictly larger. And here we have an interesting pair of relations then, because you can write the recurrence at m minus 1, and you can write the recurrence at m, and they share a lot of terms, which makes them suitable for comparison. And indeed, over here, we have this inequality here, and recall that p is a strictly increasing function because it is all the coefficients are positive, and you only consider values of x that are positive. So this inequality implies this inequality. And if we now use this inequality and compare across the two expressions and cancel out the common terms, it implies that am bigger than am plus k, which contradicts the assumption that am is where the minimum occurs. So what went wrong that led to this contradiction? Well, the only place that went wrong is essentially we assume that we can write this thing down, which means we assume like this stuff here, right? Well, obviously we can fix the issue of tie by saying that I'm going to take the index that is the smallest index where the minimum occurs. So I can always ensure that I don't have a tie. So, and this whole logic will carry through and we still get contradiction. So it must be the case that the problem is assuming that the minimum happens somewhere off the front of the sequence, right? If we have m equals 1, we will not have this issue here. So once we think through this line of reasoning, it will lead us to the very first lemma that we want to prove in the official solution. So the fact that the minimum always occurs at the front suggests that maybe you want to show that an must be increasing. By increasing here, I mean it can stay constant. So I meant like non-decreasing. It can be constant or increasing. So the logic of showing this lemma is very similar to what we have explored before. The equivalent way of showing the lemma is to say that for any L greater than or equal to 1, if I look at the sequence starting at AL would be the minimum among all these sequence of terms. And to show this, we just use the logic from the previous slide. Suppose not. Then let M be the minimum index such that AM is minimum among AL onwards. The fact that we suppose not means that this minimum index where the minimum occurs cannot be at L. So that's why M is strictly bigger than L here. Which means I can look at the term before that. AM minus 1 makes sense. So I write down my two relations. The term before that makes sense. And it is strictly bigger than this because I prevent ties by looking at minimum index. And then I have this inequality, which gives the required contradiction. So it looks like all this motivational talk that we had before that leads to a very first observation that is both natural, but also it is quite restrictive and gives us quite a bit of understanding of what a valid sequence must look like. And once we have this lemma shown, the very natural next question then is to ask how fast can then this sequence be increasing? Can it be increasing at an increasing rate, for example? Or can it only increase at a constant rate? Or can it increase like arbitrarily? Well, if we look at the recurrence relation, you can get some intuition on how to proceed. The thing is, if the sequence increases at some crazy increasing rate, then we might imagine that possibly we could run into some problems because this will be some steps above an, and it will get the steps will get wider and wider, which might suggest that it will grow faster than a kth order polynomial. So this is just some motivation that maybe the sequence cannot be increasing like crazily. There must be some control to the rate of increase. And indeed, this motivates why we want to prove the next lemma, that maybe the successive difference is bounded. So once again, to prove this lemma, we'll want to investigate the behavior of the polynomial. It seems that the growth of the polynomial will control how fast the terms can grow. And one way we can control a polynomial is as follows. It turns out that there exists an integer c such that px is less than x plus c to the power of k for all positive x. It's quite easy to show that such a c exists because if we look at the expansion on the right, it's a binomial expansion. We can easily get all the binomial terms bigger than all the small c's by making capital C arbitrarily large. So we can indeed find this bound. And you might ask, why do I even bother finding a bound of this form? This will be clear once we look at the next step. So we do have this k power here, an plus 1 power k. By the fact that the terms are increasing, we have this inequality. And this is precisely our polynomial, which we have bounded here by this inequality here to be an plus c to the power of k. And now why it makes sense to consider this form is because we now have powers of k, and we can take the kth root and move the an over, and then we have successive difference is bounded by c. So this is the proof of our lemma. It's a very elegant proof. But more importantly, we now have even more information on how a nice sequence must behave. And this is very powerful because what does our picture look like now? Let's consider a very natural block, which is an and then the next k terms. Let's look at this block. If we think about the difference of the terms from an, we see that, well, this is a jump of at most c, a jump of at most c, a jump of at most c, and so on. So di will be at most I times c. And this is very good. It seems that there's some control over this block. But it turns out that in a slide later, it will become clear why we want to consider one additional term in our block. So I'm going to be investigating the behavior of blocks that are of the form an plus the next k term, but also one more term after that. And so in essence, for each value of n, I'm going to look at the difference values d1, d2 until dk plus 1. Okay? And the thing is that each of these differences, as I mentioned earlier, they are bounded, di is bounded by ic. So there's only finitely many possible appearances of what this difference list can look like. So in particular, some lists of this must appear infinitely many times. Say this list is one of the lists that appears infinitely many times. I'm going to call any of those infinitely many values of n that give this list a boring n. Okay, so what now? For such boring n's, I'm going to put in the recurrence relation here. The thing is, for boring n's, I know what the differences are. The differences are given by the di primes. So I can write all these terms in terms of an and the di primes. So I have this expression here which only has an involved. This means that if I look at this polynomial expression here, this has infinitely many solutions because each of the an gives a solution to this polynomial equation, which means that this polynomial must equal the polynomial on the right hand side as polynomials. So we have pretty much force px to be of this form. But if I just use this polynomial itself, I won't be able to deduce what form di prime must be. I cannot constrain what di prime is. This is why I want to look at the recurrence relation when it's shifted by 1. And in this case, if I shift this by 1, this an plus 1, an plus 2, an plus 3, and so on. And once again, very conveniently, because my blocks here that I've examined do have the extra term at the end, I can still replace all of the an plus 1 until an plus k plus 1 in my recurrence relation in terms of an and di primes. Right? So, for example, this is an plus 1 and so on, then this is an plus k plus 1. And so once again, this polynomial expression here has infinitely many solutions, so they must be equal. The two sides must equal as polynomials. So now I have two polynomial identities on my hand, and maybe a comparison of them will be able to give some relationships between the di primes. And indeed, the fact that this polynomial is written in a factorized form suggests that we should examine the roots. And the roots of px in this form is very clear, it's minus di primes. If I compare to the roots of this, then we can basically shift the graph of px to the left by d1 prime to conclude that the roots of dx plus 1 prime the roots here shifted to the left by d1 prime. So these are now the roots of this expression. But on the other hand, if we look at the factorized form here, the roots of px plus dy prime are given directly by minus d2 prime, minus d3 prime, and so on until minus dk plus 1 prime. So these are the same things. This set of roots must equal this set of roots. And of course, recall that the di primes are in increasing order because they are gaps that are getting wider and wider. So we have these inequalities and these inequalities, and these two multi-sets of values coincide. So this tells us that they match, the corresponding terms agree. So if d1 prime is given by some number d, then d2 prime is twice of d1 prime, which is 2d. Then d3 prime is d2 prime plus d1 prime, which is 3d, and so on. So in essence, the di primes are basically multiples id. And of course, d here is greater than or equal to 0 because your differences are, they need to make this sequence here non-decreasing. So if we substitute back the values di prime equals to id, we get px equals to this expression. So actually we are almost done already because in fact, if we put back the di primes into our blocks, right, we see that am to am plus k form an ap with common difference d for any of these boring value m. And once you have a block of ap, you hypothesize that this forces the rest of the sequence to be aps, forward and backwards. And indeed, you can very easily prove the claim that a1, a2, and so on is therefore an ap with common difference d. And I'll just sketch how you would prove the forward and backward induction, but it's very easy to write it out. But in essence, if you want to go forward from am plus k onwards, you just take a look at the last term of this expression here and rearrange the front terms down so you get this. And then by induction hypothesis, these parts are all ap of common difference d. And after you plug in the polynomial expression, you can show that this next term continues to obey the ap behavior. And backwards as well, I will not go through the details, but if we have a chain that follows the ap behavior and you plug in the polynomial for the term before that, the fact that this is strictly increasing means there's only a unique solution, and you can check that the AP term before that satisfies this equation, and so it must be the case that the AP behavior continues to extend backwards. So anyway, you can work out these details yourself, but the crux of the matter is that once you have this AP, you are basically done, and the final last step is to check that indeed if you have A1, A2 is AP with common difference d greater than or equal to 0, then it will work. And that corresponding polynomial that makes it work is given by this. So what do you think of this problem 3? I think it's actually really interesting, but it is a motivatable problem. It is not like an impossible problem in some of the previous years. I know a lot of contestants have had fun working on this problem, but some also felt that this is easier than a usual P3. So I don't know. I thought it's actually quite involved and there's a fair bit of ideas in it. So let me know in the comment section what you think. And that's all for the day 1 problems. Do stay tuned to the channel for the day 2 solutions, which should be coming up in a couple of days. Do subscribe to the channel for more math videos, and see you soon.